Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Cauchy's integral theorem verification for problem number 3. So, today I am going to verify the Cauchy's integral theorem for the given function f of z. Now, what is the actual statement of Cauchy's integral theorem? If f of z is analytic on and within a closed contour C, then the line integral of that f of z along that curve C is 0. So, in some problems, we can apply the Cauchy's integral theorem to evaluate the line integral. Whereas, in some other problems, it may be required to verify the Cauchy's integral theorem. So, some function f of z will be given, along a curve C will be given. Now, we need to verify the Cauchy's integral theorem. That means, we need to find LHS, that is integral f of z dz along the curve C, and our final answer must be 0. So, which is the RHS of the statement. So, here I am going to verify the Cauchy's integral theorem for one more function, which is 3z square plus iz minus 4 along a square with vertices 1 plus r minus I and minus 1 plus r minus I. Coming to the solution part, given, so what is the given function? F of z is 3z square plus iz minus 4. And the curve C is a square with vertices z equal to 1 plus r minus I and z equal to minus 1 plus r minus I. Now, first we need to identify the points of which are the vertices of this square. Now, we know that z is x plus iy. This is the general form of a complex variable. Now, here the first point z equal to 1 plus I. Here 1 plus r minus I minus 1 plus r minus I. So, if you take this point z equal to 1 plus I, compare with this, the real part x equal to 1 and the imaginary part y is also 1. Therefore, the point is 1 comma 1. Similarly, if you consider 1 minus I, here x is 1, the real part, and y equal to minus 1, which is the imaginary part. So, 1 comma minus 1 is another vertex. Coming to this z equal to minus 1 plus I, here x equal to minus 1 and y equal to plus 1. So, the point is minus 1 comma 1. Similarly, the last one minus 1 minus I, which is x equal to minus 1 and y is also minus 1. So, minus 1 comma minus 1. So, these are the vertices of the given square. Now, if you draw the square, if you draw the graph of the given curve, you can identify the limits of integration. Now, let us draw this square. X-axis, y-axis, and now it is a square. So, now here this point 1 comma 1, this is the point 1 comma 1. Both are positive, and here you can see x is positive but y is negative. So, where is that point? 1 comma minus 1, and here x is negative, y is positive, minus 1 comma 1, and here both are negative, minus 1 comma minus 1. Now, let us denote these points by the letters A, B, C, D. So, these are the vertices A, B, C, D. Now, to verify Cauchy's integral theorem, we need to evaluate the line integral of this given function along the curve C, and finally, we need to show that the answer is 0. That means, the line integral vanishes. So, to evaluate this line integral of the function f of z along the curve C, we need to evaluate along each side of the square. What is the line integral? The evaluation of integral along the curve or any line. So here it's a square, so we need to evaluate along each side of this square, or this one AB, along BC, along CD, and then along DA. So this is equal to line integral along AB plus BC plus CA, CD plus DA. So we need to evaluate these 4 line integrals, and finally we show that the sum of all these integrals is equal to 0. Now coming to the first part, along the line AB. Now along the line AB, it is very clear that the value of y is minus 1. Here along this side y is minus 1, that is fixed, and x changes from minus 1 to plus 1. So y equal to minus 1 and x changes from minus 1 to plus 1. So here y is minus 1, y is minus 1, and here x is minus 1, y is plus 1. So the value of x changes from minus 1 to plus 1. Now if y is minus 1, dy will be 0 because it's a constant, and we have z is x plus iy, and since y is minus 1, z will be x minus I. Then dz will be dx plus I dy, but dy is 0, so simply dx. And therefore along AB, f of z dz is equal to integral x from minus 1 to plus 1, 3 into, now what is the function f of z? Given function 3z square plus iz minus 4. 3z square plus iz minus 4. So 3 into, what is z? X minus I whole square plus I into x minus I minus 4, and dz is dx. Now we need to evaluate this line integral. So from minus 1 to plus 1, let us simplify this first. 3, this is a minus b in the form of a minus b whole square. So a square, 3x square. Next plus I square, but I square is minus 1. So minus 3 minus 2ab term minus 2ix. So minus 6ix plus ix, I into x. Next I into minus I, which is minus I square, but I square is minus 1. So minus minus plus 1 minus 4 dx. So this is equal to, from minus 1 to plus 1, we can simplify this again, minus 6ix plus ix minus 5ix, and here minus 4 minus 7 plus 1. So this is minus 6. Now integrating this with respect to x, just here we are using the formula integral x power n dx is x power n plus 1 by n plus 1. So using this formula, the line integral along AB, f of z dz is equal to 3 into x square, integral of x square is x cube by 3 minus 5I into integral of x is x square by 2 minus 6x from minus 1 to plus 1. Now applying the upper limit, we get 1 minus 5I by 2, x square is 1 minus 6. For lower limit, minus sign, and again for this x cube, since x is minus 1, we get minus 1 here. Next minus, for lower limit we get plus, so 5I by 2 into this is plus 1. Now again minus minus plus 6 into minus 1. So this is plus, minus 5I by 2 plus 5I by 2 gets cancelled, and what remains here? 1 minus 6 plus 1 minus 6. So which is minus 12 plus 2 minus 10. So the line integral along the side AB is minus 10. Similarly, we need to calculate the line integral along the remaining 3 sides also. Now coming to the second one, along BC. Once again, let us go back to the curve. along BC. Here it is very clear that there is no change in x value. So x is fixed here, x equal to 1. This line itself is called x equal to 1 line. And y changes from -1 to +1. So along BC, x equal to 1 and y changes from -1 to +1. If x is 1, dx will be 0. Next, z is x plus iy. So x equal to 1, so 1 plus iy, and dz will be I dy. So therefore, along BC, f of z dz, the line integral of f of z along BC is from -1 to +1. Now what is f of z? 3z square plus iz minus 4. 3z square plus iz minus 4. So let us calculate this first. 3 into z square, 1 plus iy whole square plus I into 1 plus iy minus 4 I dy. dz is I dy. So this is I into integral from -1 to +1. Now 1 square is 1, so 3. I square y square is minus y square, so minus 3y square. 2 iy, so plus 6 iy plus I minus y, since I square is -1, minus 4. So this is I into, again simplifying, minus 3y square plus 6 iy minus y plus I minus 1. So by integrating with respect to y, here we get minus 3 into y square, integration is y cube by 3, plus 6i into y integration is y square by 2, minus y square by 2, plus I is a constant, so integral dy is y, so I into y minus y, and y changes from -1 to +1. So this is, these two gets cancelled, here 3 times, so I into, now the upper limit, already we have minus sign, and upper limit y is 1, so minus 1, and next here plus 3i, since y is 1, minus 1 by 2 plus I minus 1. This is for upper limit. Now for lower limit, we get one more negative sign. Already here we have minus, now one more negative sign, so that becomes plus, but the lower limit is negative value, so -1 whole cube is -1. Next, minus 3i minus plus 1 by 2. Now again, for lower limit we get minus sign, and lower limit itself negative, so minus that becomes plus I. And here minus y, lower limit already negative sign will be there, so minus plus, but y itself again minus, so -1. So now we need to simplify this first, -1 by 2 plus 1 by 2. So this is I into -1 -1 -1 -1 minus 4 I plus I 2i. So this is minus 4i plus 2i square. So this is minus 4i minus 2, since I square is -1. Similarly, the third one, AB, along AB is over, BC is over, now along CD. Along CD, here you see the value of y is fixed here, y equal to 1, and x changes from 1 to -1. So this is in anti-clockwise direction. So because we are moving from A to B, B to C, C to D, when we move from C to D, y changes from x changes from 1 to -1, and y is fixed, y equal to 1. So here y equal to 1 and x changes from 1 to -1. Since y is 1, dy will be 0. And what is z? X plus iy. Since y equal to 1, z is x plus I. and dz will be dx since dy is 0. So therefore, along CD, the line integral f of z dz is equal to x from 1 to minus 1 f of z dz. What is f of z? 3z square plus iz minus 4. 3z square plus iz minus 4. Now replace z by x plus I. So that gives x plus I whole square plus I into x plus I minus 4. And dz is dx. So this is from 1 to minus 1. Let us simplify this. 3x square minus 3 because I square is minus 1 plus 6ix plus ix minus 1, I square is minus 1 minus 4. Now again simplifying this, we get 3x square plus 7ix minus 8 dx. So now integrating with respect to x, we get 3 into x cube by 3 minus plus 7I into x square by 2 minus 8x from 1 to minus 1. That is equal to upper limit minus 1. So minus 1 whole cube is minus 1 plus 7I by 2 minus plus 8, lower limit minus 1, because for lower limit we get negative sign, minus 7I by 2 minus we get plus, so plus 8. So this is 7I minus 7I by 2 cancel, and 16 minus 2, which is 14. So we have evaluated the line integral along 3 sides of the square, and fourth one is left along DA. Along DA. So D to A. Here it is very clear that x is fixed, minus 1, and y changes from 1 to minus 1. X equal to minus 1 and y changes from 1 to minus 1. Now, if x is minus 1, dx will be 0 and z is x plus iy. The same story repeats. dz equal to dx plus idy, but dx is 0. So, dz is idy and z is x is minus 1 plus iy. So, we can consider iy minus 1 as z, and along dA f of z dz is y from 1 to minus 1. What is f of z? 3z square plus iz minus 4. 3z square plus iz minus 4. Now, this is 3 into z square iy minus 1 whole square plus I into iy minus 1 minus 4, and dz is idy. So, again simplifying this, I into 1 to minus 1. Let us simplify this first. I square y square. I square is minus 1. So, minus 3y square plus 3 minus 6iy plus I square y minus I into I square y minus I minus 4 dy. So, therefore, along dA f of z dz is equal to I into integral from 1 to minus 1 minus 3y square minus 6iy plus I square is minus 1. So, minus 1 minus 1 into y minus y, then minus I, and 3 minus 4 is minus 1 dy. So minus 3y square minus 6iy minus y minus I and then minus 1. Now integrating with respect to y. So this is minus 3y cube by 3 minus 6i into y square by 2 minus y square by 2 minus y into I minus y from 1 to minus 1. So here I into upper limit is minus 1. Already here we have minus, and y cube minus 1 whole cube will be minus. So this becomes plus 1. Now minus 3i, next minus 1 by 2, and next here plus I plus 1. Now for the lower limit we get one more negative sign. So minus minus plus 1 by plus 1, 3 gets cancelled, so plus 1, minus minus plus, so 3i. Now for lower limit again we get minus, so plus 1 by 2, and again here minus y is there. So for lower limit we get plus I, and again the same. Now here minus 3i plus 3i, minus half plus half, then I into 1, 2, 3, 4 plus 2i. So which is 4i plus 2i square, but I square is minus 1. So 4i minus 2. So hence we have evaluated the line integral along each side of the square. Now the line integral along the square, or that means along the given curve, will be calculated by adding all these 4 line integrals. So now the line integral along C f of z dz is equal to along OA, along AB, along BC, along CD, along DA. Now along AB, the first one is minus 10, then minus 4i minus 2, minus 10 minus 4i minus 2, then third one is 14, fourth is 4i minus 2, 14, 4i minus 2. So minus 4i plus 4i gets cancelled, and here 14 minus 10 minus, and here 14 minus 10 minus 12 minus 14. So which is 0. Therefore, the line integral along the given curve is 0. Hence, Cauchy's integral theorem is verified for the given function f of z. So in today's session, we have verified the Cauchy's integral theorem for the given function. That means we need to evaluate the line integral along the given curve and show that the line integral vanishes. That means equal to 0. So in the next session, I am going to discuss about the Cauchy's integral formula and the difference between these two, when we have to apply the Cauchy's theorem and when we have to apply Cauchy's integral formula. That will be discussed in the next class. Thank you very much.